Hi everyone, welcome back. This is Earth and Space Science 101, and we are now on lecture 8. So we're going to continue our unit on minerals and rocks, and our first two lectures in this unit were on minerals. So today is when we move on to talking about rocks. We'll begin with the rock cycle. We'll then continue on talking about igneous rocks. We'll also be talking about igneous rocks in the next lecture as well, mainly in the form of talking about volcanoes. And then after that, we'll move on to sedimentary rocks and metamorphic rocks. So for the next handful of lectures here, it's going to be all about rocks. So we'll start that with the rock cycle. The rock cycle and rocks in general are going to be really important, mainly from our perspective as creatures that live on the surface of the Earth. A lot of these different types of rocks form closer to the Earth's surface. But if you were to drill down through the crust and get closer and closer and closer to the mantle, you'd find out that most of the crust is actually igneous rocks, and you have this sort of thin veneer of sedimentary and metamorphic rocks that appear closer to the surface. So let's start with a definition of the word rock. A rock is a naturally formed, consolidated material. And the way that that differs from our very strict definition of a mineral is that it doesn't necessarily have to have a specific composition. There could be a range of compositions and a range of minerals. It's usually consolidated, and that means that there are several minerals that might make up a single rock. And most of these rocks are going to be composed of more than one mineral, although some can be based on just the one mineral. There's a sedimentary rock that we're going to talk about later called rock salt, and that's a pretty good example of a rock that's only really formed from one mineral specifically. So without that very limited definition of a mineral, we can start to include some more things in the definition of a rock than we could in the definition of a mineral. Even things that are organically derived, like shells and leaf matter, that kind of stuff, can even form rock in our definition under the right set of circumstances. Things like coal and limestone are composed in a large amount of stuff that was previously alive or organic material. So whenever we talk about rocks, the rock cycle is inevitably going to come up. And this is going to be something very important to kind of focus on and to get a feel for, because as we go into all of these different types of rocks, as we talk in more detail about igneous and then sedimentary and then metamorphic rocks, kind of getting a little bit of a feel for how the rocks are going to change from one type to the other is going to be really important to put all of this in perspective. So as we journey through the rock cycle, let's start with one rock in particular. Let's start with igneous rocks, and maybe a specific type of igneous rock that we've already talked about that makes up most of the continental crust, granite. A granite is a rock that has cooled and crystallized underneath the Earth's surface. So it cools and crystallizes intrusively. After it does this, that magma is going to cool, solidify, harden, and then all of these unique individual minerals are going to form and grow quite large. And then eventually this rock might be exposed on the Earth's surface, and we would then call it granite. That granite can be converted into then a sedimentary rock, a metamorphic rock, and even melted and resolidified to form a different igneous rock, all under the right circumstances. So let's assume that the first step in the rock cycle is going to be that we're going to take that granite and then turn it into a sedimentary rock. The way this happens is by all of these natural processes on the Earth's surface, breaking down that rock, breaking it into pieces, acting upon all of those pieces through chemical weathering, through water flowing in and around this rock, to change its composition a little bit and to break up all of these individual minerals into a more stable form of those minerals at the Earth's surface. So the quartz in granite would largely remain the same. It would just break down into smaller pieces and round out to form sand. The feldspars and the biotite in that granite would break down over time and change chemically to form some things called clay minerals. So what was once one solid whole rock, this granite, is going to eventually form clay and sand. And that clay and sand is going to be moved and redistributed across the Earth's surface through flowing water and moving ice and even potentially wind to other places on the Earth's surface where it's going to be deposited and then buried over time. If you bury something like sand, clay, even organic material that makes up something like limestone, if you bury that material enough and overpressure it enough, then eventually that is going to form a rock all in its own right. It's going to be a reconsolidated rock that we would then call a sedimentary rock because it's formed of sediment, stuff that was pieces of pre-existing material. That sedimentary rock could then be converted into a metamorphic rock if it was buried further. If you took that sand and that clay and buried it down deep enough, then eventually you would reach depths and pressures where the rock wouldn't completely melt, but those minerals would then recrystallize. And there wouldn't be any space left between one mineral and the next because that mineral would have essentially recrystallized and taken over that space. So the sandstone might turn into quartzite. The clay minerals might form something like a slate or even maybe a schist. Eventually, you could even bury that material deep enough where the temperature would then take over and melt the rock completely. And then once that melt resolidifies, that would then form an igneous rock again. So we've basically just taken something like a granite and run it all the way through the rock cycle. And this happens again and again over the eons of geologic time. So as we go through these different rock types, it's maybe important to stop for a second and focus on a definition for each one of these types of rock. Let's start with igneous, because this is the sequence of which we're going to be talking about this in the lectures. And we're going to start with igneous rocks today. Igneous rocks, by definition, have to be formed from a rock that has been completely melted. Not something that's been partially melted, because that would still fall into the domain of something that could be a metamorphic rock. And we'll talk about that in a little bit more detail later. But igneous rock, the word igneous actually comes from fire in the Greek. So that has to come from a rock that's in a completely molten state. And in order to melt rocks, you need temperatures between 300 and 800 degrees Celsius. That would be similar to talking about temperatures in excess of 1,000 degrees Fahrenheit on average to melt rock. So this is going to happen mainly deep below the crust, and in some isolated circumstances that molten material can make its way up to the surface in the form of lava, recrystallize there, form extrusive igneous rocks. So whatever the case, the important thing to take away for now is that for igneous rocks to form, that rock has to originally be in a completely molten state. If that melt is underground, it's magma. If that molten rock is at the surface, we then call it lava. It's the same thing in two different environments. The next type of rock that we're going to talk about is sedimentary rock. And sedimentary rocks form from pieces of pre-existing material. Now, most of the time, these are actual solid, legitimate pieces. These are things like pieces of sand and gravel and mud and clay, all basically differing only in terms of grain size. And then when you take that material and put it all back together, bury it deeply enough, it's overpressured enough, it squeezes those minerals together, they're cemented together over time by flowing water through the rock, and you have a reconsolidated rock in its own right. You have the classic interpretation of what a sedimentary rock is. As we'll learn in more detail later when we focus exclusively on sedimentary rocks, if you have rock that has been dissolved into water, and that's essentially what seawater is, it's water that has a lot of other types of rock dissolved into it, then it's possible for some of those minerals and some of that rock that's dissolved into the water to come back out again. So the opposite of having something dissolve into a fluid like water is to have it precipitate back out. And that's how you form things like salts and limestones. Those are going to be chemical precipitants, and precipitants are another example of sediments in sedimentary rock analysis. So when we deal with sedimentary rocks, we'll have to remember to include that as part of the definition of sediment and part of the definition of things that could form sedimentary rocks. So sedimentary rocks and even metamorphic rocks mainly form a lot closer to the Earth's surface than igneous rocks do. But metamorphic rocks kind of are sort of a weird one to kind of understand. It's sort of a gray area, in a sense, between sedimentary rocks and igneous rocks. Igneous rocks have to form in a completely molten state where that melt reconsolidates or solidifies, I should say. Metamorphic rocks don't have to reach those same temperatures where you completely melt the rock. You have an increase in temperature and pressure to the point where the minerals that might be in that rock aren't stable anymore, and then they recrystallize. So it's always been really fascinating to me that this doesn't actually require completely melting the rock or necessarily even melting the rock at all to reach these kind of temperatures where you can recrystallize the material and you can end up with something completely different. If you put a mudstone side by side with the metamorphic equivalent of that mudstone, you would see that these two rocks have very, very little in common anymore. Most metamorphic rocks are actually quite beautiful, shiny, full of micas and everything. And all of this comes from taking all of those same elements that might have been in the parent rock, whatever was metamorphosed to form this daughter rock, and recrystallizing it through that increase in temperature and pressure. So in the very, very layman sense, to form a metamorphic rock, this is basically like taking some pre-existing rock and cooking it. You don't have to necessarily melt chocolate chip cookie dough in order to make a chocolate chip cookie. You've just stuck it in the oven under a higher temperature, and you've changed the substance of the thing. You've changed the texture of the material without actually changing its composition. So there you have it, the rock cycle, and our first few, our overview of the types of rocks that are composing the Earth. So that's igneous, sedimentary, and metamorphic. Like I said, today our main focus is going to be on igneous rocks. We're going to start to introduce igneous rocks and go through a little bit about how they're diverse, how we begin classifying them, and then we'll talk about specific cases with igneous rocks where they form at the Earth's surface, or i.e. volcanoes. We'll talk about that in the next lecture. So while we're talking about igneous rocks, it's important to remember, and I can't say this enough, that they have to have formed from an initially completely molten state. In order to form something that's truly a granite, a basalt, a rhyolite, a diorite, or 1,000 other different types of igneous rocks, all of those rocks had to at one point be in a completely molten state. So when that molten rock cools and solidifies, you form these individual minerals. But depending on exactly where that material cools and solidifies, you might have more or less time for those minerals to cool and crystallize. And that's going to make all the difference in the world. You can basically have exactly the same material, exactly the same starting material, molten rock with exactly the same composition, and you can allow some of it to cool slowly over millions of years deep below the Earth's surface, and you'll get an entirely different texture, entirely different size of crystals than you would if you took that exact same material and cooled it quickly on the Earth's surface. So the location and the speed, the resultant speed in which they cool, is going to make all the difference in the world when we're talking about igneous rock classification. In fact, this first picture that I'm starting you guys off with today is of one rock that has cooled very slowly underground. We're going to call that an intrusive igneous rock. And one picture that is an extrusive igneous rock, one that's cooled very quickly at the surface. So intrusive rocks are also in some cases called plutonic rocks. And I like this term because it kind of gives you a little bit of a sense of the origin of this word. And hopefully it might help you sort of remember what this word means. Intrusive or plutonic means that this cools under the Earth's surface, inside the Earth. The word plutonic comes from Pluto, who is the Roman god of the underworld, the equivalent of Hades in the Greek mythology. And so it kind of gives you a sense of these fiery temperatures and great pressures and underworld, deep under the surface sort of locality where all of this rock would have initially formed. So intrusive or plutonic, those are synonyms. You can use those basically interchangeably. These rocks are going to form when molten rock underground cools and solidifies. Our name for that molten rock when it's under the Earth's surface is called magma. So magma and lava are basically the same thing in two different locations. So magma is going to cool and solidify to form intrusive rocks, and when it does, it typically cools and solidifies in huge pools underground, possibly with surrounding pre-existing rocks. Like let's say you might have slabs of sandstone and shale and limestone, and this igneous rock, having in some cases a lower overall density, will rise up through these pre-existing rocks and cool and solidify in these basically sort of big underground molten rock lakes. So when it's a particularly large igneous intrusion, we typically refer to these as batholiths. Smaller intrusions could be dikes or sills, depending on their orientation, with pre-existing sedimentary rock layers. Dikes typically move perpendicular to these pre-existing layers. They move against the layers. Sills flow out along the layers themselves, sort of like throwing sand along a windowsill and seeing it all spread out evenly. So all of these different environments are just places where intrusive igneous rocks could potentially form. The important thing to take away from this is what kind of texture they are ultimately going to have, which is essentially going to be large individual crystals. And we'll look at that in all of the different igneous rock textures in a few more slides. But first, I wanted to go into the other basic type of igneous rock. If it's not intrusive, if it doesn't cool slowly underground, deep under the surface of the Earth, it has to cool quickly at the surface of the Earth. And so the opposite of intrusive or inside the Earth would be extrusive, exiting the Earth. The other word that we use for this is volcanic, because whether or not it actually forms a traditional volcanic structure, anytime you have molten rock exiting the Earth, you are essentially forming a volcano. You have volcanic activity taking place. So when that happens, whether it's deep under the ocean on the ocean floor or at the Earth's surface on top of the big island of Hawaii or on top of the continent, this lava is going to cool very, very quickly. So when you're taking this rock from its source, where temperatures might be, again, in excess of 1,000 degrees Fahrenheit, and putting it out onto the Earth's surface, where temperatures are going to be far, far lower, or even on the bottom of the ocean at the seafloor, where temperatures are going to be even lower, that rock basically is going to cool almost instantaneously. Where you would usually have thousands, if not millions of years for the rock to cool and crystallize, the crystallization takes place over seconds to minutes to maybe as long as hours, but usually not even that long. And then that lava is going to cool and solidify. The lava, again, is this term that we're using to indicate the difference in where that molten rock is. If it's on the Earth's surface, we're calling it lava, so you can have something like a lava flow, but you don't refer to lava being underground. That's magma. So once it cools out on the Earth's surface, whether it's at the seafloor or on top of the continent, running off on the surface, that lava does tend to flow. It can flow fast or slow depending on its overall composition or its viscosity, a term we'll talk about in a little bit more detail later. But there does seem to be a little bit of a flow to it. So extrusive igneous rocks typically form in thin layers, very similar to the way that most sedimentary rocks actually form. So if you have a little bit of trouble with this magma versus lava thing, I have kind of a fun little way of trying to remember the difference. You've probably all heard of a chocolate lava cake. Chocolate lava cake has sort of a molten interior, so when you cut into it, you get all of this gooey chocolatey material inside. But think about it before it's cut as a chocolate magma cake. It's not until after it's cut and the chocolate is actually running out all over the plate that it's actually a chocolate lava cake. So chocolate magma cake, chocolate lava cake. We get this idea of intrusive versus extrusive igneous rocks. Intrusive rocks forming from the crystallization of magma. So that would be sort of similar to taking that chocolate magma cake and sticking it in the freezer, and then ultimately that isn't going to be in a liquid state anymore, but a little bit more slowly. And the chocolate lava cake is after you cut it and after it flows. So when we're talking about intrusive versus extrusive igneous rocks, it's very important to be able to talk about the result of these rocks having cooled and crystallized either extrusively or intrusively. And the main thing that's going to be different between the two is not its composition, because that composition is going to be the same. That magma versus lava, it's going to have exactly the same overall elements within that, but it's going to have a very different overall texture. The size of the crystals is going to be the main thing that differentiates an intrusive versus an extrusive igneous rock. So some of the intrusive igneous rock textures include a phaneritic texture, which is a fancy way of saying it has visible crystals, because phaneros is Greek for visible. It's a term or a prefix that we're going to see later on in the semester when we're talking about different time periods. When we talk about the Phanerozoic, that's going to mean visible life. That's the time period where visible life was around. Phaneritic texture means that the crystals are actually visible without the aid of something like a microscope. So phaneritic textures usually have large, nice visible crystals, and all of those crystals are relatively large. Or in some cases, you might have a pegmatitic texture. When you have an igneous intrusion moving through the subsurface and moving up towards the surface and cooling and crystallizing, the very last stuff to form is going to cool the most slowly. And if it cools very, very slowly, then the crystals get to be really, really huge. So typically with a pegmatite, or something that has a pegmatitic texture, the individual crystals are going to not be like a millimeter in diameter. They might be as big as my hand. They're going to be extremely large. So you get a lot of really nice gemstones and pegmatites. You get really nice large individual minerals and large individual crystals because of the length of time that those crystals have to grow. So again, intrusive textures include phaneritic and pegmatitic textures. And the overall takeaway of all of this is that the crystals are all going to be large. You don't have some smaller crystals and some larger ones. All of the individual minerals will be visible if it's an intrusive igneous rock. Extrusive igneous rocks, or volcanic igneous rocks, are going to almost exclusively have invisible crystals. So these are individual minerals and individual crystals that are going to be so small that most of the time you need a microscope to be able to see them. So sort of the classic texture that's associated with extrusive igneous rocks is an aphanitic texture. And I think of aphanitic as basically anti-phaneritic. If phaneritic is visible, then aphanitic is invisible. It means all of them are very, very small. They look smaller than individual grains of sand, and you would have to actually look at it under a microscope to discern one mineral from the next. In some cases, you have a few minerals that grow extremely rapidly in extrusive igneous rocks. So you might have a handful of larger crystals and an otherwise microcrystalline matrix. So you would get something that kind of looks like a chocolate chip cookie. You would have individual chocolate chips that are large, and you can see that that's an individual chocolate chip, but the rest of it is a combination of ingredients and very, very, very small textures. So porphyritic texture is going to have mainly microscopic crystals with some overall larger crystals. So again, the big takeaway here is at least some, if not all, of the crystals are going to be very small in extrusive igneous rocks. All of the crystals will be large, or at least visible to the naked eye, in intrusive igneous rocks, plutonic igneous rocks. So that's our first major division, our major way of classifying igneous rocks. You can basically take all of these different types of rocks that we have, all of these different igneous rocks, and we can basically put them in a category based on where they formed. And that tells us a lot. That's a very, very important piece of information. It even relates all the way back to plate tectonics. If we know that, for instance, the makeup of the ocean floor, a basalt, is something that cools extrusively, then we know that that rock had to have actually come from below the ocean floor to cool and crystallize at mid-ocean ridges. We know that the continents are mainly intrusive igneous rock. They're going to cool and crystallize below the surface, whereas all of these surface processes are going on above them, forming sedimentary and metamorphic rocks. So intrusive versus extrusive is our first major way of classifying rocks. But we can also classify them based on something else entirely. So you can have intrusive and extrusive varieties of several different igneous rock compositions. So the compositions can range from having a lot less silica and more heavy elements and some metals, and having a lot of silica and fewer overall heavy elements and minerals and metals. So the rock chemistry is going to be the thing that differentiates all of these different compositional classifications in igneous rocks. And the most important part of this compositional classification is going to be the amount of silica that's present. That's going to be the thing that really defines the difference between a mafic rock and a felsic igneous rock. So to understand this in a little bit more detail, I've kind of created a table that gives you some of these different compositional terms and what kind of chemistry you can expect in the rock and the overall appearance that you can expect in the rock based on that chemistry. So the two terms that we've already heard at the second of our two mineral lectures was felsic and mafic, and those are the two major chemical classifications for igneous rocks. The minerals that make up those rocks are either felsic or mafic. But you can have an intermediate igneous rock that's intermediate in composition between felsic and mafic, and you can even have something called ultramafic. And ultramafic rocks are typically not found in the crust at all, or at least very, very rarely. These are rocks that mainly make up the mantle. So these are our overall igneous rock compositions, ranging from the most silica, those are going to be the felsic igneous rocks, to the least amount of silica, which is the mafic and then even the ultramafic igneous rocks. So rocks that have greater than 65% silica, that's silicon and oxygen, those are typically felsic. 50 to 65% are intermediate rocks. 45 to 50% are mafic, and then anything that has less than 45% of its overall composition based on silica, that's going to be ultramafic rocks, and those aren't found in the crust very often at all. So while the mantle might have less than half of its overall composition in silica, the crust has a much higher abundance of silica because you have the felsic and intermediate rocks to kind of balance it out a little bit. The other elements that are going to be present besides silicon and oxygen in felsic igneous rocks will almost always include some potassium. That's the thing that really sticks out and really helps you to be able to identify felsic minerals as opposed to mafic minerals, but also aluminum and sodium too. You'll have aluminum and sodium present in intermediate and even in some mafic igneous rocks, but you typically replace the potassium with calcium instead. It's a heavier element, and it's going to be more abundant as you get closer and closer and closer to the mantle. You don't typically have any sodium, potassium, or calcium almost at all in the mantle, and your other elements besides silica in the mantle are going to be almost entirely iron and magnesium. Now, okay, going back to that potassium, this is the real key element that's only found in the felsic igneous rocks and not in intermediate and mafic rocks. That potassium leaves behind a very sort of obvious effect on the rock itself. If an igneous rock has a lot of a sort of salmony pink color, it almost undoubtedly has a fairly large amount of potassium in it, because potassium typically makes things that sort of salmony pink color. Potassium feldspar, potassium present in other minerals as well, it typically leaves behind that signature of making things pink. So, it's easy to kind of think of this as a light to dark scale in the overall compositional appearance of igneous rocks, where granite would be, or any felsic rock would be, almost completely white, and ultramafic rocks would be completely black. But that's not quite the case given the elements present within those minerals. So felsic igneous rocks typically have, some fairly light elements, some white to gray and some black minerals, but a lot of pink in there as well. And that helps you identify the felsic igneous rocks. Intermediate rocks typically have a lot of combination of light and dark minerals. Mafic rocks, mainly all much darker minerals. So these rocks are going to have the appearance of overall being almost entirely black. And then ultramafic rocks are often going to be green because of their iron composition. Whenever you have minerals that form outside of the effect of the Earth's atmosphere, so deep under the surface and deep down in the mantle, where you don't have a lot of oxygen in the atmosphere present to oxidize the iron and to make it red, the effect of having iron present in the rock is to actually make it green. So it kind of gives you, it's kind of a fun thing to think about if you kind of step away from this table for a second and just kind of stop and think about what does the mantle actually look like. It's probably green, glassy, and granular, because olivine, the principal mineral that's going to compose ultramafic rocks, has that appearance when we have it at the Earth's surface. So think about minerals maybe 1 or 2 millimeters in diameter, that are going to be roughly kind of roundish, not very squarish, kind of roundish, making up almost the entirety of the mantle. Those are all going to be ultramafic minerals. So now, it's really important to kind of step back, take away, because we've covered a lot of material here. We essentially have 2 completely separate ways of classifying igneous rocks. We have intrusive and extrusive varieties of all of these different compositions, with the exception of ultramafic rocks. Ultramafic rocks don't really have extrusive equivalents, because these are rocks that are going to make up the mantle. There are no extrusive rocks in the mantle. There's no volcanic rock in the mantle. This is going to be rock that, if it does move all the way up to the Earth's surface, it's going to sort of remain intact, and these pieces of the mantle are going to be brought up to the surface. So let's kind of scratch ultramafic rocks and really just concentrate on the 3 crustal igneous rock compositions. That's felsic, intermediate, and mafic. So we have 3 compositional terms, and you can have intrusive and extrusive varieties of those 3 rocks. So you can have an intrusive variety of a felsic igneous rock, that's granite for the most part. You can have an extrusive variety of granite that's called rhyolite. You can do the same thing with intermediate rocks. You can have the intrusive variety of an intermediate rock, which would be diorite, or the extrusive variety of that same composition, that same stuff cooling quickly on the Earth's surface, would be called an andesite. If you have a mafic igneous rock that cools under the Earth's surface, it's not very common, but it does occur, that rock would be called a gabbro, and the extrusive variety of it would be called basalt. So that's 6 overall igneous rock names. Not all are going to be important to remember and to take away. And in class, we'll go over which ones are going to be present on tests and all that kind of stuff. But 6 overall possibilities based on 2 textures and 3 compositions. Now, we've already talked about 2 of these being extremely common in the Earth's crust, the continental crust being made up of mainly felsic intrusive igneous rocks, that would be the granite, and the oceanic crust being mainly made up of extrusive mafic igneous rocks, that's a basalt. So we can already tell that 2 of these are going to be far more common and far more important than the rest. But what I want to talk about next is why those are common and important, why we have this crust that's mainly made up of these two rocks and not all of the other types of igneous rocks. And then finally, why we do have this continued diversity, why you do have things occasionally like gabbro and diorite and rhyolite, and where those rocks are going to form. So this is probably the most complex subject that we will get to in all of Earth and Space Science 101, but it's also one of the most important, because otherwise I'd probably skip it. If it was just another kind of piece of information to cover, I would probably skip it. But you could definitely handle this. It's just kind of worth a little bit of a warning going into it that it's not immediately intuitive. You do have to kind of spend some time with it and look at these charts in a little bit of detail and really think about it. But right now we're going to get into the reason why we have all of this diversity in igneous rocks. Because again, generally speaking, the more mafic extrusive rocks are going to form the oceanic crust. Intrusive felsic igneous rocks are going to form the makeup of the continental crust. But we do have all of this other diversity. So the reason why these are going to be more common, and the reason why we have this other diversity, is because of 2 things. This is really going to allow for the diversity in igneous rocks that we see, the commonness of granite and basalt, and the whole reason why we have different igneous rock compositions to begin with. It really all boils down to two things. One we're going to talk about today. The next we're going to cover in the next class period or the next lecture. The one we're going to cover today is something called Bowen's reaction series, and it deals with the crystallization sequence of minerals, the fact that minerals are going to crystallize out of a melt in a predictable order. So that's going to be our subject for the rest of class today. And in the next lecture, we're going to talk about the role of plate tectonics in having various igneous rock compositions. So, like I said, the first thing we're going to talk about is what's called Bowen's reaction series, or the crystallization sequence of minerals. So you can basically kind of just write Bowen's reaction series on the page, crystallization sequence of minerals, and not really understand at all what that means. So I've got plenty of analogies, plenty of metaphors to kind of help this make a little bit more sense. But the first very important thing to take away from this is that not all minerals are going to have exactly the same melting temperature. The main substance that we're used to talking about melting and freezing and the kind of temperatures that we see on the Earth's surface is water. And all water on Earth, no matter where it is, it's going to melt or freeze at 32 degrees Fahrenheit or 0 degrees Celsius. The rocks that compose the Earth's crust, both the continental crust and the oceanic crust, are made up of many different minerals, and every single one of these minerals is going to have its own melting temperature. That means it also has its own temperature where it's going to freeze or resolidify or crystallize. All of these terms, all of those verbs are as work as well as the next one. So the geologists that figured this out, that rocks that compose the Earth's crust actually have minerals that all melt and crystallize at different temperatures, was named Bowen. And so when he went through this process of melting different rocks and seeing which minerals are going to melt at which temperatures, which ones are going to crystallize at which temperatures, he figured out that this crystallization sequence has a lot to do with the complexity of the silicate structures that those minerals contain. And the overall sequence that he was able to create from high temperature to low temperature of the order in which these minerals crystallize became then known as Bowen's reaction series. Okay, so let's set that aside for a second. This all gets very abstract. It's very weird to think about because we don't like talking about temperatures that we can't really see expressed on the Earth's surface. That's kind of weird to think about. It's very weird to think about two different rocks in the gravel in your driveway melting at different temperatures when we kind of think about it all as uniform material. So let's settle that aside for a second and think about something that is a little bit more applicable to us. We're going to figure out the Bowen's reaction series, the crystallization sequence of something that you can melt a little bit easier given surface temperatures. We're going to talk about the melting sequence and the crystallization sequence of something like a Snickers bar. So I love food analogies, as you probably figured out already. There have been several in just this lecture alone. I've talked about the lava cake and chocolate chip cookies, and now I'm talking about Snickers bars. So I'm a little hungry today, too, so I'm sorry. So the Snickers bar is going to be a great analogy of the melting of a rock because a Snickers bar is made up of various ingredients. It doesn't just have caramel or just have chocolate or just peanuts. It's made up of all of these different things. So all of these different components of a Snickers bar are going to basically sort of act as our analogy for the minerals. And the Snickers bar as a whole is going to be our analogy for the rock. So while the rock might be something like a granite, and that granite might be composed of plagioclase, feldspar, quartz, biotite. The Snickers bar is going to act as our rock in this analogy, and the components are going to be things like caramel and nougat and chocolate. So that's sort of the beginning of our analogy here. And now what Bowen did and what we're going to do is melt it. The easiest way of melting something like a Snickers bar would then be to put it in your mouth. If you happen to have a Snickers bar around and you want to actually do this in real time, then you'll be able to kind of see how all of this works. Whenever I've taught this class in a regular classroom, I like to actually bring a whole bunch of little fun-sized Snickers bars, and everybody can kind of do this together. So if you don't have one with you, you can at least sort of imagine it. You can think like, okay, now I'm going to put the Snickers bar in my mouth. What happens? The first thing that is inevitably going to melt, the easiest thing to melt given lower overall temperatures, would definitely be the chocolate. Chocolate's going to melt at the lowest overall temperature. It's going to melt first. So in our melting sequence, we're going to put that one first. First is chocolate. Now, I've kind of run this this lab, if you will, this experiment in class a few times before, and I get different results. Some people say the nougat melts next, and some say the caramel does. It's a little harder to identify, but I'd say more people have told me that the nougat is probably the second thing to melt. So we'll say it's chocolate and then nougat and then caramel. The last thing to melt, and it doesn't actually melt at all in your mouth, you'd need much higher overall temperatures, would be the peanuts. So there you have all of these different ingredients making up one thing and all melting in a different sequence. So if we could run this in reverse and crystallize all of these substances, the opposite of the melting sequence would be the crystallization sequence, or if you like to think about it this way, the freezing sequence of the Snickers bar. The first thing to crystallize out, to form, to solidify, would be the peanuts, and then the caramel, then the nougat, and then eventually the chocolate. So hopefully that kind of gives you a little bit better sense of what the Earth's crust is like. It's not like putting an ice cube in your mouth where that ice is going to melt all at the same temperature, all at the same time. It's having a lot of different ingredients that all melt at a different temperature. Now, the real Bowen's reaction series includes all of these common rock-forming minerals that we've already talked about. Things like olivine and pyroxene, plagioclase feldspar, potassium feldspar, quartz. And they all melt at very precise individual temperatures. And that same temperature that they melt is the same temperature that they would crystallize in. And that's what we really care about because we're looking at how they form and not necessarily how they're going to be destroyed. So from the top down on Bowen's reaction series, you have the crystallization of lots of different minerals, but they don't kind of work out perfectly in a perfect line. They actually make up two different branches of this crystallization sequence. So ignore everything on the right side of this image for just a second. Let's focus on what's labeled as the discontinuous branch of Bowen's reaction series. This is going to be the one that's a little bit easier to understand. Starting at a fairly high temperature, roughly around 1200 degrees Celsius, which you don't need to memorize, but just to kind of give you a little bit of a taste for what high temperature means in this case. The first thing that's going to crystallize out of a melt is the most simple of all the silicate structures. It's going to be the isolated silicate structures that make up something called olivine. And then all of the iron and magnesium and silicon and oxygen that can form olivine will crystallize out. All at that temperature, all at that time. It's going to crystallize out all of the olivine that it can. And then once the temperature is lowered past the point where olivine is typically going to crystallize, olivine stops forming. That's why it's called the discontinuous branch, because you cut off the formation of olivine and move on to pyroxene. The pyroxenes are slightly more complicated. They make single chain structures. It takes a little bit more time to form that mineral and for all those atoms together to form all of those minerals. So the single chains form, lots and lots of these little chains of silicon and oxygen, in addition to stuff like iron and magnesium and calcium. Then once you crystallize out all the pyroxenes and the temperature continues to lower, you might next reach double chains. Those are the amphibole minerals. And then once you form all the amphiboles, then you would form the sheet silicates, the biotite. And as you're going down Bowen's reaction series and going through all the crystallization of all of these different minerals, you're changing your overall composition of the melt that is left behind after all those minerals crystallize out. So once you get rid of all the olivine and the pyroxene, you're no longer having a composition of magma that has mafic minerals left to be crystallized. All the stuff is going to be intermediate. And then all the intermediate minerals kind of crystallize out. And then you're just left with everything that's left behind, which would be felsic. Eventually, you're left behind with things like potassium feldspar and quartz. Meanwhile, there's a continuous branch where other minerals are going to form all around the same time, and you're going to get this sort of phase out of the calcium-rich plagioclase feldspar, and you're going to phase in sodium instead of calcium. So there's this sort of sliding scale, this big gray scale between the plagioclase feldspar that's rich in calcium to the plagioclase feldspar that's rich in sodium. And eventually you're going to be left with only the sodium end member of those minerals. So to kind of conceptualize what this looks like in real life in the crust, picture magma that's rising up from the mantle and moving up towards the Earth's surface, moving up through the crust and making its way up towards the Earth's surface. The very first thing to be crystallized out and to be left behind way down in the mantle is going to be all the stuff like olivine, all of the ultramafic material. And then as you get towards the base of the crust and temperature lowers a little bit more, because temperature is going to lower all the way towards the surface, you get pyroxenes and amphiboles and the plagioclase feldspar in the continuous branch. Those are going to be the mafic and intermediate rocks. And then finally, whatever's left behind, still deep down below the surface, that's going to be the felsic igneous rocks. They're going to cool and crystallize last in this sequence. They're going to be the sort of all the stuff that's eventually left behind and then has to crystallize out because the temperature continues to drop and continues to drop. So this temperature range is from around 1200 degrees at the top of this crystallization sequence to the lowest temperature forming closest to the Earth's surface, which is going to be closer to around 800 degrees. That's Bowen's reaction series in a nutshell. And if it were just Bowen's reaction series, if it was just, here, let me tell you about the crystallization sequence of these different minerals, then I, again, probably wouldn't cover this at all, except it has extremely important implications for what the crust of the Earth is ultimately made out of. And what the Earth is made out of is what we have to work with, what the life in general has to work with. So essentially, you can go back all the way back to Bowen's reaction series to explain the existence of the continents and the oceanic crust and the reason why the Earth is structured the way it does. It has very important overall implications. So the main thing that's going to change between the high temperature mafic to ultramafic igneous minerals that are going to form in Bowen's reaction series is going to be that those are going to have relatively less complex silicate structures. And then as you move towards the low temperature end of things, the last stuff to crystallize out of a melt, the stuff that's going to take the longest to crystallize out, those are going to be the ones that have the most complicated silicate structures. The complexity of the silicate structure is going to tie in perfectly with the durability of those minerals and the durability of the rock that results. So when the material that makes up the oceanic crust occasionally forms things like volcanic islands, some examples of that would be the Hawaiian Islands or the Indonesian islands, they're relatively short-lived. That's all made out of stuff like olivine and pyroxene and calcium-rich plagioclase feldspar. So those are going to have less complicated silicate structures. That means they're going to be less resistant to erosion, and those islands might only be around, especially if they're not on an active tectonic plate boundary or active hotspot, they might only be around for a couple million years. And when we're talking about millions of years, that's nothing in terms of geologic time. We need things that can stand up to the length of Earth history if we're going to actually build civilizations on the continents. We need things that are going to be around for billions of years. The continental crust, made up of the more complex silicate structures, the framework silicates and the sheet silicates, stuff like biotite, quartz, potassium feldspar, and sodium-rich plagioclase feldspar, those are going to be far, far more durable because of the complexity of their silicate structures. And those are going to be the minerals that form the rocks that make up the continents. And the continents exist for billions of years, mainly because they're super, super durable to the erosive forces on the surface of the Earth. The oldest overall continental crust is on the order of 3.7 billion years old. And while you have some younger crust than that, having the cores of these continents be that stable overall is important for actually being able to build really sort of anything that extends up above the oceans on Earth. Another way to kind of close this out and to think about it that becomes really important is to kind of compare Earth with Bowen's reaction series to Earth if it didn't really have Bowen's reaction series. If you didn't really have Bowen's reaction series and all of these different minerals just crystallized out all at once at a high temperature, we would basically have water world. We would not have stable continents at all. And that means life would never have actually evolved out onto the continents at all, because those continents just wouldn't be there. So instead, we have an Earth that has, roughly 30% of its surface covered in continents. And that means like creatures like you and me, and terrestrial organisms in general can exist on those continents. It's a very important overall topic. So we're not quite done talking about igneous rocks yet. In the next lecture, we're going to be talking about the role that plate tectonics plays in the formation of igneous rocks. And then we're going to go on to talk about volcanoes, volcanic structure, lava, all that kind of good stuff. So it should be a lot of fun. Until then, keep rocking.